talk by Jennifer Perdigao, and she might talk about what to do with these materials if we ever get them back to Earth. So, Jennifer, please, the stage is yours.
And I think actually my colleague Jared, he's going to start off the first part of the presentation.
Okay, yeah, that's fine.
And Jared, are you on?
I had to unmute there.
Oh. Okay, it's all yours, Jared.
All right, thank you very much. So just by way of an introduction, my name is Jared Schneider. I am an attorney. I work for Tressler LLP out of their Chicago office. And my colleague works out in the LA office. And I won't try and explain her background, but I'm an aviation attorney. I specialize in aviation matters, and I also have a great interest in the space travel and all aerospace matters. So that's another reason why I'm here today. So what we're going to be discussing is asteroid mining, space debris and how that's related to asteroids, and planetary defense. And what we're going to do here is break this up into two sections. I'm going to start by giving kind of a background to some of these matters, and some of it might be recapping and a little bit basic information. And I'll definitely touch on some stuff that other people discussed today, but hopefully it'll be a nice refresher. And I think that that will set up a nice segue for Jennifer to talk about kind of some of the legal issues. So if we could go to the next slide. So again, a little bit basic here, but asteroids, it's a Greek word for star-like, and as has been discussed, they're essentially rocky objects that orbit the sun like planets, but they're much smaller. They're also referred to as minor planets or planetoids. And also, as has been discussed, the vast majority of these are found within the orbit, the main asteroid orbit, which is between Mars and Jupiter. But there are other orbital families as well, as not all asteroids are located in the main belt. For instance, there's the Amur asteroids, which travel inside the orbit of Mars, but also reach near Earth's orbit. There's the Aten asteroids and the Apollo asteroids, which both have orbits that crosses the Earth's orbit. These are referred to as near-Earth asteroids, or as people have discussed, NEOs or NEOs. There's also a subtype of this, which is called easily retrievable objects. And essentially, those are objects that it's been determined that they could be transported into more accessible orbits at affordable costs, of course, for exploration and mining purposes. So if we could go to the next slide. So asteroid mining, why is it that people and corporations want to mine asteroids? Well, it's because they're very resource-rich space rocks, essentially. And they contain various elements and minerals, some, as you see here, like gold, platinum, iron, titanium, water, hydrogen, nitrogen, oxygen, and nickel. If we could go to the next slide. So there's also classifications, which was also touched on briefly. And so individual asteroids are classified by their composition. And primarily they're made out of mineral and rock, but there's three main categories that asteroids fall into. And that is the C-type, S-type, and M-type. As you can see, C-type asteroids, which make up about 75% of the known asteroids, these have a high abundance of water, organic carbon, and phosphorus. The C stands for carbon. S-type asteroids are the second most common, and they make up about 17% of known asteroids. They're brighter, and they have numerous metals inside, including nickel, cobalt, and more valuable metals like gold and platinum. The S refers to silicates. They also contain some iron and magnesium silicates, which is stony, and that's where this name comes from. And then there's M-type asteroids, and the M stands for metallic. These asteroids are fairly bright, and most of them are comprised of pure nickel and iron. M-type asteroids are rare, but they contain about 10 times more metal than S-types. And of course, the sizes of these asteroids vary significantly. Next slide. So mining purpose and potential. So one potential purpose is to extract and ship valuable metals back to Earth. And we'll talk a little bit about this. It was just recently touched on, and hopefully I can help answer that question that was posed. Early evidence suggests that there are trillions of dollars worth of minerals and metals buried in asteroids. And it's theorized that essentially the Earth's reserves could become exhausted at some point. So people have suggested maybe going up and taking some of these resources and bringing them back to Earth. Additionally, asteroids have been referred to as the stepping stones to the solar system. Other people have referred to them as galactic space stations and cosmic pit stops. And this is just what was being discussed a moment ago. The idea here is that more likely mining is going to allow us to further explore space and the solar system. It'll make human space travel easier and cheaper. The water can support a space colony potentially. C-type asteroids, which have water, can be used for exploration efforts beyond just that asteroid where they're located. The water could, of course, be broken down into hydrogen and oxygen to form rocket engine propellants. And then that would reduce the costs of missions and trying to travel further out into space. C-type asteroids also have key ingredients in fertilizer, which could be used to grow food out in space. So overall, the purpose is that, and the potential is that it'll incentivize the development and infrastructure and allow us to transport more easily within the solar system and beyond. Again, iron metals and other common ones can be used for construction, like building structures in space, or even other aircraft. And some say that it could provide data for the search for extraterrestrial intelligence. So if I could go to the next slide. Actually, I think if you could back up just one more. So here's just some general mining options. And it's been theorized that what could be done is that we could bring raw asteroidal material to Earth and use it here. We could potentially extract the material on site and then ship those processed materials back to Earth. And of course, we could potentially produce propellant at that time for the return trip. Or we could transport the asteroid to a safe orbit around the moon or the Earth or near the International Space Station. And this has kind of been seen as the most economical, as it should allow for most of the material to be used and not wasted. And of course, it costs a significant amount to transport these materials back and forth. So as discussed, it might not be feasible or economical to bring materials back to Earth. So the next slide. So these are just a few of the possible extraction techniques that are discussed. There's surface mining, which is basically scraping materials off the surface of the asteroid. Shaft mining, which is basically tunneling into the veins of the specific substances and then extracting the material through those shafts. Magnetic rakes. So asteroids with high metal content may be covered with loose grains that could be gathered up with magnetic rakes and then stored. There's also a heating process where whereby water and other volatiles could be extracted using heat. And then the MOND process, this is specifically for extracting nickel and iron. It involves passing carbon monoxide over the asteroid at certain temperatures and high pressures. And this forms a nickel and an iron gases, which from there we can extract the nickel and the iron from the gas. Next slide, please. So this is kind of a list of some potential targets. They're kind of considered the best targets for mining, given the cost to benefit ratio. Bennu, which you'll see there, Bennu has been discussed. This has an estimated value of $700 million and potential profits, if it was mined, they've estimated to come out at about $200 million. And I'm sure most of you have probably heard Neil deGrasse Tyson was quoted as saying, the first trillionaire will be the person who exploits natural resources on asteroids. So you can see if, way down the line, if this does become, a process, we could see a trillionaire based on the value of some of these asteroids and what's contained therein. Interestingly, Bennu is the subject of NASA's first asteroid sample return mission. It's targeted for this October 20th for the first sample collection attempt. And it's also scheduled to return to Earth in September of 2023. Also, you see at the bottom, 16 Psyche. NASA's Psyche mission is targeted to launch in August 2022. It's supposed to arrive there in early 2026. And the goal here, among other things, is to determine whether or not its core whether or not it is the core of an earlier planet as has been suspected. Next slide. So I also wanted to talk a little bit about space debris because these two kind of are tied together. So space debris, which is also commonly known as space junk, space waste, or space pollution, has been defined by NASA as defunct human-made objects in space which no longer serve a useful function. Space debris has basically persisted ever since the beginning of the space race and back when the Soviets launched Sputnik in 1957. But it's not confined just to artificial space debris. If I could go to the next slide. So artificial space debris refers to things that are potentially left up in Earth's orbit, like non-functional spacecraft, abandoned launch stages, mission-related debris, and fragmentation debris. And some of these, for instance, spent rockets disintegrate through time and they erode, and through collisions they create more debris, and then you're left with the debris floating around in certain orbits. Another example of artificial space debris is kind of interesting. Just yesterday during the spacewalk that was discussed earlier, one of the astronauts lost his mirror. It was like a 5-inch by 3-inch mirror that was attached to his suit, and he lost it and it floated out into orbit. But in addition to artificial space debris, there's also natural space debris, and this can be found throughout all regions of space. And some of this are meteoroids or fragments from comets or asteroids. Next slide. So just to briefly talk about the locations of space debris, there is so there's Earth's orbit, which is geocentric orbit, any object orbiting around the Earth. And there's also 3 other types of orbit that have been defined: high Earth orbit, medium Earth orbit, and low Earth orbit. Next slide. So High Earth orbit is, this is an orbit with an altitude higher than 35,000 kilometers or I think 22,000 miles. And this is an altitude, the altitude of geosynchronous orbit. That's where the orbital period matches the Earth's rotation. So in high Earth orbit, orbital periods are greater than 24 hours. Objects at this altitude move less than 1,000 miles per hour. And this is kind of a rarely used orbit for our purposes. Next slide. Then there's medium Earth orbit, and this is found at a distance between 2,000 and 35,000 kilometers. Essentially, it's more than 1,243 miles above Earth's surface, and it's below geosynchronous orbit. Satellites in this region have orbital periods ranging from about 2 to 24 hours, and it's also the home to a lot of navigation or specialty satellites. Next slide. And then, of course, there's low Earth orbit, and this is where most satellites are located. NASA's Earth observing system is here. The International Space Station, of course, the Hubble telescope, and Mir was at one point located in this orbit. Next slide. So this is also the orbit where most space debris is concentrated. And many asteroids or their fragments exist here as well. This is an orbital period of 128 minutes or less, which means that an orbital velocity needed to maintain a stable low Earth orbit is about 17,000 miles per hour. So you can imagine what an object moving at 17,000 miles per hour could do if it, collided with a space station or another asteroid. Next slide. Additionally, SpaceX's Starlink satellites are being placed up in low Earth orbit. This is the constellation that Elon Musk is putting together to provide global broadband internet. Today, there are 538 satellites in orbit. They launch about 60 satellites at a time, and they're planned to have more than 1,200 satellites in low Earth orbit. And as you might have heard, just yesterday, they were planning to send up another Falcon to deliver some, but that got scrubbed. I think it's now set to launch tomorrow. Next slide. So the amount of space debris, it's truly unknown. In 2019, it was estimated that there were nearly 20,000 artificial objects in orbits above Earth, which includes 2,200 or plus operational satellites. But these are just the objects that can be tracked. It's believed that there are more than 128 million pieces smaller than 1 centimeter in diameter that are out there. Additionally, 900,000 between the size of 1 centimeter and 10 centimeters, and 34,000 pieces larger than 10 centimeters. Next slide. So this is just kind of a quick chart that shows the proliferation of this debris over time. You can see how it's grown. And then there's two very large spikes that are interesting in 2007 and 2019. The one in 2007 represents more than 3,000 large pieces of debris that were created when Chinese anti-satellite test that purposefully destroyed a weather satellite was used. Additionally, the jump in 2009 was due to the accidental collision between a US and a Russian satellite. But you can see how those numbers have grown significantly. Next slide. So of course, we're trying to track these, and there's a couple different, there's actually a few different organizations doing it, but some to mention here: the Space Surveillance and Tracking System the European Union uses, and then there's the Space Surveillance Network, which is operated by US Strategic Command. And these programs basically catalog and track these objects, but at the same time, their capabilities are somewhat limited and at the moment, they can't necessarily track objects that are 10 centimeters and smaller that are located in low Earth orbit. Next slide. So what exactly is the threat here? Well, artificial debris poses a growing threat to functioning satellites. But natural debris like asteroids and their fragments also pose a threat. Existing asteroids and fragments may collide with other asteroids or other artificial debris or other satellites in low Earth orbit. And these EROs, easily recoverable objects, they're considered likely candidates for mining. And there's been plans put in place to relocate some of these asteroids to low Earth orbit. And depending upon how they do that, if they don't contain all the dust or all the materials while they're mining, well, then these particles could potentially escape during the mining process, which creates more and more debris. And if there's too much debris, at some point, it could prevent the use of the orbit in general. Next slide. So as I was discussing, more and more space debris leads to more potential for impacts. And this has been mentioned earlier too. The Kessler Syndrome which is also called the Kessler effect. This was proposed by NASA scientist Donald J. Kessler in 1978. And it's basically a chain reaction theory whereby, you know, these objects in high enough density will collide with each other, and that will create more debris and a chance for more and more collisions. Eventually, if this occurs, it could render the orbit useless, and some say potentially impassable at some point. Next slide. So just to touch on kind of the next topic here, near Earth or objects, or NEOs. These are any small solar system body which orbit brings it into the proximity of Earth, and their orbit crosses Earth's. And if the object is larger than 142 meters across, it's considered a potentially hazardous object, PHO. Most known PHOs and NEOs are asteroids. And other than space debris collisions, these objects pose another threat, which is their potential impact with Earth. Next slide. So orbital changes can lead to collisions with Earth, which has been theorized. And essentially, these elliptical orbits, or the trajectories of the asteroids, could be altered in time by the gravity of, say, another orbit from an asteroid or another planet. And even one that we expect may miss Earth could change trajectory and eventually make its way here. The 99942 Apophis, this is an asteroid with a diameter of 370 meters. This caused a very brief period of concern back in December 2004, because initial observations of this indicated that it had a probability of 2.7% that it would hit the Earth on April 13th, 2029. Luckily, however, improved predictions have eliminated that that collision will occur. Of course, it will eventually return and will have to be monitored for future potential collisions. So if I could go to the next slide. So asteroid impact avoidance. Just briefly going to touch on a couple of these. There's a number of methods that have been theorized or starting to be put in place, which could somehow divert or prevent the destruction that an impact would create. One of these is called Space Guard. It's the name for some loosely affiliated programs which are working together to discover, catalog, and track asteroids and anticipate their trajectories. NEOCAM is a relatively new mission. It's an infrared telescope, and it's being used to track and access the risk that asteroid may have. And a side note, it's also being used to scan asteroids for exploration and mining. Kinetic impact is another way. I think Jennifer will touch on this briefly too, but NASA's DART test, which is Double Asteroid Redirection Test, is going to go up and potentially see if they can deflect an asteroid. And then there's a couple other possibilities, which is capturing small objects, moving them to on better trajectories, nuclear-powered lasers, nuclear explosions to try and throw asteroids off their course, and then spacecraft propulsion, which is this idea where we could potentially, attach onto a asteroid and propel it into kind of a different trajectory. So on that note, I will turn it over to my colleague, Jennifer.
Thank you, Jared. Slide. What I'm going to go over is the general legal framework for the use of space. And Jared was discussing the issues with space debris and asteroid mining. And there is a kind of a framework under which the international community in the United States operate. And so I'm going to start with the international treaties. If you get me to the next slide, that would be great. So in 1967, a number of countries negotiated and agreed to the treaties on the principle of governing the activities of states in exploration and use of outer space, also called the Outer Space Treaty. And then that was followed by the Convention on International Liability for Damage. And that really required that the nation state that sponsored the mission that caused damage to property or people would be liable for that damage. And then the Convention on Registration of Objects, that requires that if one of your citizens or citizen companies is launching from your country, they have to register it, and they have to register it as a citizen of the United States. Therefore, if that causes any problems, if upon launch it ends up landing in another country instead of making it to orbit, or if it hits another satellite, the United States is responsible for that damage. So, and then finally, I'm going to touch on the Moon Treaty. The Moon Treaty is not signed or ratified by the United States, Russia, or China. So it really doesn't have any kind of effect on us. And it really is looked at as a failure in international law, because if those three countries are not going to sign off on it, then it really has no true meaning to it. So if you could go on to the next slide. So we're going to take a look at certain articles of the Outer Space Treaty. And these are the purposes, treaties are highly negotiated and they're very political. And so they end up being very vague. And also, if you think about the climate in 1967, you're in the middle of the Cold War, you don't have nearly the technology. I mean, the advancements we've made since 1967 to date, they couldn't probably even begin to realize where we were going to be at this point. But this is what we're operating under. So, and this goes to the liability portion. This is where state parties to the treaty shall bear international responsibility for national activities in outer space, including the moon and other celestial bodies, whether such activities are carried on by governmental agencies or by non-governmental entities. So this makes the United States liable for launches by SpaceX. And when I say liable, I mean to the international community. And then also Article 7 makes them liable for the actual damage. And let's go to the next slide. So within the treaty, there are various international guidelines. And you know, obviously with space debris, you have the issue of, with the amount of satellites and the amount of satellites that are no longer operable, are they going to run into other satellites? And so as it continues to get more crowded up there, they've outlined the various guidelines and standardization for operation and launch. Next slide. Also, the United States has obviously its own national space policy. And first we have Congress passed the Commercial Space Launch Competitiveness Act. And actually for the purposes of this presentation, I'm only going to touch on two parts. One part now based on the orbital traffic management. And this, at this time, the Congress initiated a study where for the study of orbital traffic for the purposes of orbital debris mitigation. And this act actually kind of outlines a lot of how they're going to go forward in space. And one of the things they did was to preclude the FAA from regulating space launch to the extent that it regulates aviation. Now, FAA still regulates, you still have to be licensed by the FAA to launch. You still have to show that you can get the rocket up there, and you have to, and if you're bringing it back, you have to have safe re-entry, and you have to meet all of the requirements before they issue a license. But as you may all know, it's much stricter when it comes to like, aircraft in the United States, and it comes down to specific certifications on the airplane. But because space is still, it's still new, and it's still, space exploration is still very new, and as they don't want to preclude development and innovation, so the FAA has been halted from making further regulations until 2023. If we could go to the next slide. And these are additional debris mitigation standards that they have that have come down. And then the purpose of these is to obviously just to monitor and to prevent orbital collisions. And thing is, the damage that would be caused by a collision, they're so expensive that I think their focus has been on mitigation. There haven't been actually a lot of actual liability issues that have arisen, because I think at this point they see the problem, they're trying to deal with it, and I think mitigation is probably the best way to go if that can be done. Obviously, at some point things don't always go as planned, so that you do, that's why you have the legal framework to deal with it should that occur. Okay, next slide. So these are just some examples of FAA regulations. You have of things you have to show to get a license from the FAA to launch, and this is just an example. This is not an exhaustive list, and but essentially, you have to be able to show that this can be safely launched, and if you're bringing anything back, the re-entry, that will be safe. And the FAA needs to protect the public and property. At this point, they have no obligation towards like astronauts. Astronauts are they're assuming the risk because this is still experimental. This is still new. And if the FAA was going to go through regulating that, we'd never get off the ground at this point. So there's still going to be a lot more that needs to happen before the regulations, although that it could end in, they could start regulating in 2023 if that's not extended. All right, go next slide. The FAA is not the only governmental agency that will regulate space launch. The FCC also has a number of a number of statutes because obviously there's communication satellites, and so they also have to be involved, and they also care about their assets. So they also have their own guidelines for the mitigation of orbital debris. So next slide. And even NOAA has its own regulations concerning space debris. So, you know, that's the one thing, when once our country starts regulating things, everybody gets involved. Anyway, next slide. So just to show you, demonstrate how legal liability works under the Outer Space Treaty, there's been really only 3 potential cases here. And the first one was the 1977 Cosmos 954. And this was a Soviet satellite with a nuclear reactor core that landed in Canada. Canada spent $12 million cleaning up. I think even the United States paid another $3 million to help get it cleaned up. Canada sought $6 million contribution from the Soviet Union for the damage caused. And ultimately, under the treaty, the Soviet Union ultimately paid $3 million. And, you know, they were taking the position that it wasn't really their fault and something else hit them that caused the accident. So ultimately, it was a negotiated settlement. So in 2009, there was an iridium collision with an inactive Russian satellite and a US communication satellite. But here, I mentioned the registration convention earlier. You are required to register your launch and satellite with the host nation. They did not register it. Since they didn't register it, they didn't actually have a claim under the treaty. Therefore, the parties actually settled outside the framework of the liability convention. And finally, in 2007, the Chinese ASAT test, they blew up their own satellite, which actually caused 35,000 pieces of space debris. So which now that's in orbit. So that just increases the amount of debris that's up there that obviously could cause additional issues. And in January 2020, there was a near miss between non-operational satellites. The next slide. Okay, so now we go to asteroid mining. Because I know a lot of people have talked about asteroids hitting the Earth, but that's more of, for lack of what we would say in legal profession, that would be an act of God. I know that's probably not how you all phrase it, but that's not something that liability-wise anybody caused. But mining could actually cause problems, and Jared talked about those, because you're actually adding to the debris. If you're retrieving things from orbit or from outer space, then and bringing them back, you run the risk of causing damage to property, other satellites, and people. So the question is, under the treaties and the framework we have, is asteroid mining legal? Well, definitely, maybe. And what did they mean in 1967? So next slide. Probably in 1967, they didn't actually think about the ideas of asteroid mining quite yet. And so essentially, it kind of depends how you read the treaty. So it's supposed to be space. They agreed that they would make it would benefit for all mankind. And it would be free for exploration and use by all states. So the question is, what does that mean? And if you move, let's go to the next slide. But specifically under Article 2, the moon and other celestial bodies are not subject to national appropriation by a claim of sovereignty, by use or occupation or any other means. So the question is, what about the resources contained therein? So we can't go establish that, okay, the moon now belongs to the United States. We can't do that. We agreed to that. But the question is, what about the resources contained therein? And that's subject to interpretation. Now, the Moon Treaty that I mentioned earlier, which is not signed by the it's not signed by the United States, Russia, or China, so it really has little effect. But in that one, that specifically prohibits the harvesting of those resources, except through an international regime established to govern the exploitation of such resources when it becomes feasible to do so. So had they signed it, arguably that they would have been precluded from doing that. But they didn't sign it, and China didn't sign it, and Russia didn't sign it. So it really, again, has no real effect. So let's go to the next slide. So this is going back to the Commercial Space Launch Competitiveness Act. And this part of it has been kind of referred to as finders keepers. So this permits United States citizens that go and, they get their license, they launch their vehicle, they do their mining, or they go collect samples. If they extract them, they get to keep them. That's the current state of the law. So under that, if they can figure out how to do it, then they're welcome to do it. Next slide. Now this is just an interesting case because a U.S. space they landed one of their I can't remember what it was, like one of their little spacecraft, and apparently Gregory Nimitz had made a claim for ownership of asteroid 433. He recorded this claim with the Archimedes Institute, and then he filed his claim with the state of California under the Uniform Commercial Code, who apparently actually registered it. So when the spacecraft landed on asteroid 433, Mr. Nimitz actually sent NASA a bill for 20 cents a year, prepaid a century in advance. So I think the total bill was for $20. Well, obviously NASA didn't pay that bill, and Mr. Nimitz filed suit against the US, but the court dismissed the action because there's nothing under US law or any international treaty that establishes his right to assert a private property right on an asteroid. And in fact, the United States has already agreed to be bound by a treaty that says, no, you can't actually assert ownership or sovereignty, that type of thing, over the moon and other celestial bodies. So that was dismissed. He actually appealed, and of course it was thrown out again. Anyway, next. So, and going back to the liability issues under asteroid mining, if there are damages caused by mining, the liability would fall on the state that has responsibility for the entity conducting the mining operations. So if you're trying to extract things from outer space, you cause additional space debris, you take out a satellite, your nation state is ultimately responsible for that. And then they're responsible for regulating it in case they need to seek damages from you. All right, next. So one of the things that Ken had asked us about, which is kind of outside the scope of legal type of issues, is what are they doing for disaster response? I think somebody touched on it earlier, that if something came right now, we probably don't really have anything in place to deal with it. But they have started doing exercises, and NASA did put together an action plan for asteroid disasters in June 2018, which outlines certain goals of what they need to accomplish. And next slide. And NASA and FEMA have actually done a number of exercises as to how they would respond to an asteroid disaster or the threat of an asteroid disaster. And this basically kind of includes collection, analysis, and sharing of data, the simulation of a potential asteroid event, observation, deflection, and analysis of an impact of footprint models. So what actually do they think will happen on the ground? How many people will be affected, and the effect on the infrastructure, and how to get it out to the public, evacuation. And as they proceed, they're actually going to start including the local and state emergency response teams to make it more effective. Next slide. And finally, and I know a number of people have discussed this before, NASA will try its first double asteroid redirection test and in 2022 to try to basically essentially crash a spacecraft into the asteroid to change and to deflect it into another direction. And this is the first mission developed by NASA's Planetary Defense Coordination Office, which was established to detect and warn of potential asteroid collisions and to determine who, oh, I'm sorry, and I have a typo there, how to mitigate such hazards. So ultimately, to the extent that this would not necessarily create liability, but there is a situation once you start figuring out how to prevent asteroid disasters, then you actually start to take on a duty to prevent them if you can. So they're actually even further down the line, there could be liability if whatever you send up there to deflect it fails to deflect it. Now, initially there shouldn't be because this is still all very experimental, but that's how, but you know, there's always enterprising lawyers out there willing to stretch the law a bit. So anyway, I think I'm over my time. So I hope that was helpful. And if anybody has any questions, feel free to do them in the question and answer stage. I don't want to take any more time, but thank you so much, and I appreciate it.
Thank you, Jennifer and Jared. Very, very informing talk. Definitely somebody has to pay attention when there is damages possible from doing things. And sounds like that this is pretty much work in progress. There is a lot of stuff that still need to be figured out with space mining and consequences of space operations. What I suggest is that we'll take questions shortly after the last talk, which is coming up. And if you can stick around for just a little bit longer, we'll do a Q&A session at the end. So again, thank you so much. And I think we should be ready to move forward to Dr. Yoshikawa from Japan, directly from Japan. Is he online, Ken?
Yeah, he's online. Yeah,
excellent. Okay. So, Makoto, hello.
Can you hear me?
Yes, we can hear you and we can see you.
Okay, good. So, can I share my screen?
Yes, please share your screen and tell us a little bit about what you do, and then give the presentation, please.
Okay. Okay. Good afternoon, everyone. I am Makoto Yoshikawa. I am mission manager of Hayabusa 2. Okay, now I share. Can you see my slide?
Yeah, now we can see it clearly. Mm-hmm.
Okay. So I am very happy to talk about Hayabusa 2 today. And now Hayabusa 2 is on the way back to the Earth. The Earth return is at the end of this year. Okay. Yes, so Hayabusa 2 mission is the second asteroid sample return mission following Hayabusa. And this is a spacecraft, Hayabusa 2. And the main purpose of this mission is to study the origin of the solar system, especially to study organic matters in the early stage of solar system. And also the demonstration of new technology is important. And this is a Ryugu, very interesting object. It is a small C-type near-Earth object, and you can see the orbit of Ryugu here. This red line is the orbit of Ryugu. So Ryugu is located just between the Earth orbit and the Mars orbit. And actually, this is a position of today. So today, Ryugu is quite near to the Mars. And yes, Hayabusa 2 is also near Ryugu and Mars. So at the end of this year, sorry, at the end of this year, Ryugu will approach to the Earth here around here, and at the same time, Hayabusa 2 will come back to the Earth. Anyway, Ryugu is NEO, so this mission, Hayabusa 2 mission, is very important for planetary defense. Now I show you spacecraft. The Hayabusa 2 spacecraft is not so large. The body size is just 1 meter by 1.6 meter by 1.25 meters, very small. And the total mass is just about 600 kilograms, including fuel. It has 2 high-gain antennas. One is for X-band, the other one is for K-band. And of course, it has a solar array paddle, and this is a reentry capsule, and this is a sampler horn to get the surface material. And the main engine is ion engine, this one. And on the bottom side, we have a small carry-on impactor. This is very important instrument to create the small crater on the surface of the asteroid. We have 4 science instruments. ONC, this is an optical navigation camera. There are 2 kinds of camera. The one is telescopic, and the other one is wide angle. And this is a LiDAR, laser altimeter, to measure the distance between the asteroids and spacecraft. NEWS 3, this is a near-infrared spectrometer, and the TIR, this is a thermal infrared imager. And these are the lander and the rovers. We have mascot. This is a small lander made by DLR and CNES. And these 3 are small rovers we call Minerva 2. So we have 4 lander and rovers. And on the bottom side, we have 5 target markers. Target marker is an artificial landmark. So before landing, before touchdown, we dropped one of the target marker for the landmark. Okay, this is a spacecraft. And another thing is, another important thing is DCAM. This is a separable camera. I will talk this later. Like this, sorry. Yes, so using these onboard payloads, we can do scientific study in very wide scale range. By the 4 remote sensing instruments and the SCI and others, we can study this red area. This is a scale. This is a scale, and by using mascot and Minerva 2, we can observe the asteroid on the surface. And when we get a sample from an asteroid, we can do microscopic science. Okay, now I show you a mission scenario. Hayabusa 2 was launched in December 2014, and just 1 year later, it came back to the Earth to perform Earth survey. And then 2.5 years later, it arrived at its destination, asteroid Ryugu. The arrival date was June 27th, 2018, so exactly just 2 years before. And we made a lot of observations, and in September 2018, we released 2 small rovers, Minerva 2-1, and then in October, we released Mascot lander. All of these operations were successful. And then next is touchdown. The touchdown was very difficult, so we postponed it, and first touchdown was done in February last year. And then we did impact experiment to create the small crater on the surface of Ryugu in April last year. And second touchdown was done near the impact crater in last July. And then we released final small rover, Minerva 2-2, in October last year. And the spacecraft left Ryugu in November 13 last year. So now it is on the way back to the Earth. So and the Earth return is at the end of this year. Now I show you computer graphics of this mission scenario. So Hayabusa 2 arrived Ryugu June 2018. Yes, and then on September, we released 2 small rovers, Minerva 2-2. The altitude was about 55 meters. So very slowly, these 2 rovers went down to the surface, and they bounced like this and stayed on the surface. And then both of them hopped like this, and they took a lot of images of the surface of Ryugu. I will show you the real image later. And next thing is mascot operation. We separated mascot like this from altitude of about 50 meters, and the landing was successful. And mascot also can change its attitude like this, and it got a lot of scientific data. And next thing was touchdown, but we postponed the touchdown, and this time we separate just target marker like this. The target marker by the flash lamp on the spacecraft, target marker is illuminated like this. And the spacecraft looked at its target marker, this one. And this time, it did not make touchdown, but just going up. Okay, so next is a touchdown. Spacecraft went down to about 8.5 meters high, and it looked the target marker. And the spacecraft moves very precisely above the touchdown point. And then it changed attitude a little bit, and then just a free fall, like this. Yes, and some horn touched the surface. At that time, Barrett was shot and hit the surface, and fragments coming up. And at this time, a lot of pebbles came up too. I will show you the real image later. So first touchdown was successful. And next is a big challenge to make the artificial crater on the surface of Ryugu. It was in April last year, and the spacecraft went down to about 500 meters high and released this small carrion impactor. This small carrion impactor will explode 40 minutes later. So spacecraft quickly moves and it hides behind the asteroid. But before hiding, spacecraft released a very small camera, this one. This is a separable camera we call DCAM3. And this camera were able to observe the impact experiment. Like this. So explosion and impact. And actually, we were able to observe ejector curtain. Also, I will show you the real image later. And at this time, spacecraft was far behind the asteroid. So the spacecraft was safe. And 3 weeks later, it went back to the crater to observe it. Okay, and the next is the second touchdown. We chose the place for second touchdown near the impact crater. Inside impact crater was rather risky. Okay, so this is a impact crater, and the spacecraft touches down around here. So touchdown method is similar as the first touchdown. Spacecraft was looking at the target marker here and free fall like this. So in this region, we thought subsurface material exists. So we do hope that we were able to get the subsurface material too. Okay, so second touchdown was successful. And we have done all the mission up to here. However, we have 3 target markers left. So we made another experiment. We released 2 target markers into the orbit around the Ryugu, like this. Now, first target marker was released. Then changed the velocity of spacecraft, and the second target marker was released to the different direction, like this. So this one is a polar orbit, and this one is for the equatorial orbit. And we observed the motion of these 2 target markers around the Ryugu. So I think we will estimate the gravity potential of Ryugu in detail. And finally, we released last small rover, Minerva 2-2, into the orbit around the Ryugu. Also, we are able to observe its orbital motion around the Ryugu. Yes. Okay, so and the spacecraft left Ryugu last November, and using IO engine, spacecraft is changing its orbit towards the Earth. And the Earth return is end of this year. So still, we have many things to do. But anyway, the mission around the asteroid were successfully done. Okay, so this is a mission scenario. So now I show you some images of Ryugu. This is the first image that spacecraft took, this small dot, very small. This image was taken in February 2018. And next I show you approaching Ryugu. This is a still small dot, but it becomes larger and larger, and we can see its shape. We were very surprised to see the shape of Ryugu was a spinning top. We never imagined such shape before arriving. Yes, and this is a group photo in our operation room. So we are very happy. The arrival date is June 27th, 2018. And I am here. So this is Ryugu, very interesting asteroid, spinning top shape, and the surface was covered by lots of boulders. So we understood that the touchdown was very difficult because of these boulders. And these shows the physical observation. We estimated its shape very precisely like this. And this is a color image of Ryugu. Ryugu is very dark, a very black object. And this is a temperature, thermal data. And this graph shows the near infrared spectrum. The data of Ryugu is this one, this black line. And you can see small absorption. This absorption means that the surface material contains some water. And this is a gravity map. And these images are very amazing. These are taken by the small rover. The left side image was taken when Minerva 2-1 was hopping. And this is the surface of the Ryugu. And the right-hand side image shows the sun, motion of the sun. Very interesting image. And this is a mascot. You can see mascot here just after the separation. And mascot also took a lot of images of the surface of Ryugu, and we can do very detailed study. Okay, and this is a touchdown site selection. The site selection was very difficult because we could not find large smooth area on the Ryugu. So finally, we select this area, L08, because we thought the number of boulders is small here. And later we studied this area in detail, this one. So again, we found a lot of boulders in this area, but in this small area, the diameter is 20 meters. In this area is smooth. So we chose this area and tried to drop target marker inside this area. However, the target marker dropped just outside, about 5 meters outside of this area. This is the target marker location. So here we discussed where to touch down. One candidate is this red area, a little bit wider area, or this small area close to target marker. So finally, we chose this 6-meter area for the first touchdown because the distance to target marker is quite small. But this area is very small. The size is almost same as the spacecraft size. This movie shows the target marker release. This white dot is target marker, which is falling down. And this is a shadow of Hayabusa 2. So spacecraft is always tracking target marker. And this is a of target marker, so about 5 meters from this area. And this movie was taken after releasing target marker. You can see the surface of Ryugu well, and also I like this movie very much. Okay, so the first touchdown. This is a operation of first touchdown. At first, spacecraft went down to the altitude of 45 meters, and spacecraft was hovering here. And then spacecraft again went down to the 8.5 meters high and hovering, and a free fall and touchdown and going up. So now I show you the video of touchdown. This video was taken by the small monitor camera CAM-H. So now spacecraft started going down, and you can see this dark part is a sampler horn. This movie is 5 times faster than actual motion, so actual motion is much slow. So now it touched the surface, yes, and going up. You can see a lot of rocks came up. But anyway, the first touchdown was quite successful. And I show you another movie of touchdown, this one. This movie was taken by the wide angle camera located on the bottom side. You can see many rocks moving like this. Please see it again. Yes. So the first touchdown was successful, and the accuracy was quite high. The error of operation was just 1 meter, and we know where the sampler horn touched, this area. So again, this is a group photo. Too many people gathered in our operation room like this. And the next challenge is impact experiment. Spacecraft went down to about 500 meters high and separated small cannon impactor. And this small cannon impactor, SCI, explodes 40 minutes later. So spacecraft quickly moves at first horizontally and then vertically and hide it behind the asteroid. But before hiding, spacecraft released small camera, DCAM-3 here, and this camera can observe this impact experiment. And later, 3 weeks later, spacecraft went back to this impact crater to observe it. And one of the reasons why we create the impact crater is to get the subsurface material. However, the impact crater, the inside of impact crater is rather risky for touchdown. So we select the area near the crater for the second touchdown. So now I show you the SCI operation. This is a SCI just after releasing. And right-hand side, you can see the images just after impact. You can see the ejector curtain here, but much better image is this one. Now you can see the change of ejector curtain. And I made this movie, this one. I think this is very impressive movie. You can see the change of ejector curtain clearly. And the crater is like this. So this left-hand side image is before impact, and the middle one is after impact, and the right one is comparison. You can see clear crater here, and also you can see this big rock is moving. And the size of crater is about 15 meters in diameter. This one. This red circle is crater diameter, about 15 meters. And this black circle is rim diameter, about 18 meters. The depth of a crater from the top of rim to the bottom of the pit is about 3 meters. The size of the crater was quite large. We never imagined such big crater before this impact experiment. However, the inside of the crater is very dangerous for touchdown. So we examined the region near the crater. And this image shows that the dark color region is where the color was changed before and after the SCI experiment. So which means on this dark color region, we have material from the impact crater, which means if we touch down here, we can get the subsurface material. So we select this area for the second touchdown. So, but as you can see, there are lots of boulders, rocks around this area. And this area, the size is about 7 meters in diameter. And we were able to put target marker inside this area. And anyway, we examined these boulders in detail, like this. And we made a 3-dimensional maps, and we made a lot of simulation. And we were sure that we can do the second touchdown safely. The touchdown operation is quite similar as the first touchdown. And one difference is the hovering altitude. We make hovering altitude 30 meters instead of 45 meters. And this is a movie of second touchdown. In this case, the movie speed is 10 times faster than real motion. Again, you can see a lot of pebbles came up. Okay, anyway, the second touchdown was successful. So we hope that we can get the subsurface material too. And the accuracy was much better. The error was just 60 centimeters. And we know where the sampler horn touch. So again, this is a group photo, always same. Many people gathered in the operation room. And finally, we made this experiment. We separate 2 target markers into the orbit around the Ryugu, like this. This is a real data, and can you see the small dot moving around it? This is a real data. And also, we separate last small rover, Minerva 22, into the orbit around the Ryugu. Okay, so this is the last image of Ryugu. Spacecraft left Ryugu on November 13 last year, and the left-hand image were taken by a telescopic camera, and the right-hand image were taken by the wide-angle camera. The size of Ryugu becomes smaller and smaller, and it moves out of this view. And then it disappears from the camera angle, like this. And still, here, but also Ryugu disappears from wide-angle camera. And after that, we never observed Ryugu from the spacecraft. Again, this is the same, but the number of people in this photo has decreased. So this is a trajectory. This is a return trajectory, and the Ryugu departure is here, November 13 last year, and we did a first long-term ion range operation here, and this was successfully done. And now we are doing the second ion range operation here, and the operation will continue until the September of this year. And then we will do the reentry terminal guidance operation, and the Earth return is at the end of this year. The return place is here, Woomera Desert in Australia. Now we are discussing many things with Australian government. This area is the same that the Hayabusa, original Hayabusa returned. Okay, so yes, this is an international cooperation. We have very nice cooperation with many countries, especially in Europe, Germany and France, and the United States, and also Australia. And we have very nice cooperation with OSIRIS-REx team. We will exchange a sample between us. And this is a Hayabusa 2 joint science team group photo. This was taken in LPSC last year. We have many foreign researchers. And this is a cover of Nature and Science with many signatures. But as you know, this is not Ryugu. This is Bennu. This photo was taken by the OSIRIS-REx. And this one, Science paper, this is a Ryugu taken by Hayabusa 2. And now we know a lot of information about the Ryugu. This is a summary of its physical parameters. I think the most important parameter is density. Density is just 1.19 gram per cubic centimeter. This is very low density. So this indicates that the porosity is more than 50%. And we think that Ryugu is Lagrange object. And also the shape is very interesting, spinning top shape. And currently the spin period is about 7.5 hours. In this spin period, the shape couldn't be spinning top. So in our study, maybe the rotation of Ryugu was faster in the past. Maybe spin period was 3.5 hours. Then we can explain the spinning top shape. So such studies was done by our science team, and this is one of the results. This shows that from the shape of Ryugu, we estimate the spin of Ryugu was 3.5 hours in the past. And also, this is a near-infrared spectrometer result. This small absorption, 2.7 micron, this indicates that the material of Ryugu has some water, but the amount of water is not large. This is evolution of Ryugu. Maybe Ryugu came from some families inside of the main belt, and it has
Thank you very much, Dr. Yoshikawa. This was a spectacular presentation, and congratulations on a successful mission. Hopefully it will be successful on the last leg of return to the Earth, and very much looking forward to seeing you holding some of these pieces in your hand, which is going to be very exciting, I think, for you and for your team.
Thank you very much.
So I think with that, Ken, we should probably move to some Q&A. I'm not sure who is still online with us from the original presenters, but this is the time to have Q&A. We should probably start with Professor Yoshikawa, because it's the latest topic, and I'm sure there's going to be many questions. I'm just reading the comments that were sent on our chat room here, and they are all very, very excited about this. Really warm congratulations. I'm sure that you're going to tell us a lot more during the next Planetary Defense Conference next April. So exciting stories, I'm sure. Really an amazing presentation. So Ken, shall we go and start to see who has some questions?
Yeah, please. Yeah, go ahead. Yeah.
Okay. So I didn't have a chance to read through all of the notes here, but now it's the time to type your questions if you have any questions for any of the presenters that are online.
I'll try to bring the attendees on board and they can ask too.
Oh, sure. Okay. So if you'd like to ask in person, just raise your hand and Ken will enable you to speak.
Well, first I see this in Q&A. I think Grant has some kind of command for the space law. Did you see it? Number 3.
Yeah, I saw it, but it doesn't look like a question. It looks
Okay,
like
okay.
just a comment.
Don't worry about it. Yeah.
Yeah. Okay. So no questions from the audience, I guess. Ken?
I see. But they are still there. They are typing commands.
They are. Okay, so let's
Yeah.
wait a little bit, a minute or two to see who might have a question showing up. I have the Q&A panel open and also the chat area here.
Yeah, so I heard previous Professor McKeegan said he has something to say to Dr. Yoshikawa during your presentation.
Of course. Please go
Remember,
ahead.
he said he was looking to meet with Dr. Yoshikawa.
Okay, Professor McKeegan, you would like to say something, to speak about what you've seen?
I don't recall specifically what that was about, but I think it's a fantastic mission, and I really appreciate how clever and daring it was to do the impact experiment and go back for a second sample. This will be extremely interesting to compare to the surface sample. One question I had was, what do you imagine is the largest fragment that you can capture into the sample return capsule?
Yes, thank you for your question. I think the largest sample may be about a few millimeters size.
Great. Dr. Ishikawa, can you tell us a little bit about your lesson learned from Hayabusa 1 into Hayabusa 2? What did you learn to make that second attempt so successful?
Yes, in the Hayabusa 1 mission, we had a lot of troubles, very serious troubles. So we studied all the troubles of Hayabusa 1 and modified the spacecraft. And also we studied the way of operation. So in Hayabusa 2 case, we made a lot of simulation or rehearsal operation before real actual touchdown. So, so the spacecraft hardware became much better than Hayabusa 1, and also operation method was better than Hayabusa 1. So that's why, I think that's why up to now, the mission of Hayabusa 2 was quite successful.
Excellent, and congratulations to that. I think that it shows that persistence pays off. So you learned from the first attempt and implemented it on the second attempt, and so far it's been great success. What are your thinking into the future? So the spacecraft is coming back at the end of the year, and there's going to be many stories to tell. Do you have another big milestone that you think you might be aiming at in the coming future?
Yes, of course, the return to the Earth is the most important thing, but after that, at least the spacecraft is quite healthy and it has a lot of fuel. So now we are discussing the extended mission. We are looking for the next target of asteroid for rendezvous. So when we finish the study, we will announce the next target of Hayabusa 2.
Excellent. So that will not be a sample return. I'm assuming it's going to be in situ science, just sending data from another target.
Right. We don't have a sample return capsule, so just go to the asteroid. Yes.
Excellent. Fantastic mission. I'm waiting to hear about it in the next conference. It's going to be amazing. And the animations and the videos are also amazing. I'm almost feeling that we need to make another movie just about that mission. So maybe IMAX #2 one day. Ken, did you see any questions that were typed in for anyone?
No, but I moved them to the position they can unmute and show their video anytime they want. So in principle, they should, like Glenn, Glenn type a lot of commands. So Glenn, you have maybe can say
Hi, you guys. I haven't attended one of these conferences before, but I'm a plasma physicist at Los Alamos National Lab. I work on fusion plasmas and diagnostics. And I think actually the purpose of a fusion reactor should not be to make fusion electricity on the Earth, but in fact, if we have a working fusion reactor, it will be the primary, most excellent rocket propulsion system possible. And so that's what I hope someday we can do with a fusion rocket, because I want a fusion engine on the bottom of my rocket, and I want fusion warheads on the top so that we can deflect any asteroid or any comet on short notice. And of course, at 3 months to 6 months out, once it's by the moon's orbit, as people mentioned earlier today, it's too late. You have to do the biggest deflection you can possibly do, which is like 10 meters a second. And you need to do that 3 to 6 months out. And if you are successful, the object will still pass between the Earth and the moon. So, when you push it as hard as you can barely do a sufficient deflection. And that's with the biggest, most energetic sources that we have available on the planet today. So fusion on top and fusion on the bottom, that's the long-term solution. And it's going to take a lot of work to get to that point. But also in the intervening years, I hope someday we could practice on a real rock that we don't care about. One that's on the other side of the solar system. It doesn't matter if we push it the wrong way or how that comes out, and we can then model the effects and see the effects with an actual experiment. That's what I'd like to see. So as you guys have mentioned, we need a 3-part program for planetary defense, which includes early detection, practicing actual deflection and modeling it, and then of course getting there fast enough with a vehicle that's 20 times faster than any existing spacecraft. That's what I'd like to see long term. So I put a link up to a paper that I wrote 5 years ago with a number of other co-authors. It's in the question and answer. It's a free access paper. Take a look. I think you'll find it's a fun read.
Okay, yeah, we saw it earlier in the India today, I guess. Okay.
Yeah. Okay. A very nice conference. Thank you very much. I enjoyed it.
Oh, thank you very much for participating and for your good comments and participation in the global effort here. Yeah, I think there is a message from the National Space Society from Seth Potter. So please unmute yourself and share your screen if you would like to be seen, and go ahead, Seth. Okay, Seth had a comment here. He may not be able to unmute, I'm not sure, but he wants to mention the National Space Society, AV problems. Okay, so we'll be patient a little bit more until he figures this out. Any other questions? So yeah, go ahead. Jared, I'm seeing you now.
Oh, no, no comment or question at this moment.
Okay.
I think John, Mr. Filber has raised his
hand. Hello. This is John. Yes, I wonder if any of the speakers could comment on the feasibility of long distance lasers to vaporize the surface of an incoming object and deflect it that way? What would be the range that's feasible without the light beam dispersing too much?
I think that potentially is a good question for Madhu. Is he online, Madhu?
Yeah.
Madhu has talked about
mute.
laser. Yeah, Madhu. Do you have a good insight
Okay,
into the...
can you hear me now?
Yes.
Okay,
Loud and clear.
Could you please repeat that question, Jared?
Okay, I can repeat it myself. I'm wondering, what is the feasibility of using a long distance high powered laser to vaporize the surface of a potentially hazardous asteroid and deflecting it by the reaction force of the vaporized surface material? And what would be the maximum range that would be limited by the dispersion of the light beam?
Well, these are the areas in which work is progressing now, but the basic optical physics tells us that there are tremendous losses associated with transmission over long distances to make it possible to do this. However, there have been studies way back from the 1980s that tell us that we can take care of very small objects. I mean, seriously small objects, centimeters across, and ablate them at lower orbital distances. So the new methods that have been proposed by others, including the phased array system, allows us to use many lasers coupled together to provide the primary beam. However, again, it is an endeavor that needs more work and study. And I think all of you perhaps know about the Starshot project that was proposed by Professor Lubin at UCSB. And you may also want to look at the work of Claude Phipps, who talks about using light. To me, it is the cleanest way to approach an object without hurling material mass at it. However, we will have to spend a good deal of effort to make it viable at the distances where we can mitigate such an object. If that is helpful to answer the question,
does it make a lot more sense to have the laser in space so there's no atmospheric dispersion from an Earth-based laser?
These are things that have been studied, and I think in our slides before too, we mentioned that several policy questions remain to be dealt with. For instance, there was a study to integrate a high power laser on space station to get rid of debris approaching it. And it was shelved because of the policy issues of wielding a laser weapon in space. This is an ongoing discussion, and hopefully we will have something of that sort, a cannon that can help us during other flights when you may have to encounter an object in a short order. As you know, lasers are the big thing now in the Department of Defense because I think they've exceeded the 1 kilogram per kilowatt in equipment, which is dramatic because you're going to have handheld devices that can obliterate your enemy. But it'll be a while before we see that happening in space. There are several hurdles, policy and also technical.
Yeah, and I think I'd like to add on to that, I've seen several presentations related to space power, talking about large scale, I guess, solar panels to collect, light from the sun and convert it to electricity in a multi-gigabyte, I think, maybe even more, that could be beamed either down to Earth or beamed to anywhere. And potentially in the future, something like this could be used to, deflect asteroids or melt the surface of asteroids for other purposes. So I'm not sure if anything like this has been studied, maybe yes, but just in the, my vague memory is that there were presentations on in the multi-gigawatt space power generation in space, beaming the energy.
That is correct. That is correct, Nahum, because I think maybe, I don't know if you were in class when we reviewed a student project where she decided that she could channel off an SPS array producing gigawatts of power when needed to focus it on an approaching bolide. And I recall that project. So that is, these are interesting things because, as I mentioned, approaching a bolide, with a high energy beam, directly imposes loads on the bolide that usually we don't talk about, and if I remember Lubin's slides, he mentions that when the impact occurs, it is pretty much similar to setting off a rocket engine on the face of the bolide. So dramatic things can happen depending on the characteristics of that system. For instance, I had this question for Dr. Y. I think I just mentioned that on the running chain here. I thought the density of Ryukyu was quite low. And the first thought that I had was, could it be hollow? And because of the spin associated with it. So unusual things can happen when you focus energy directly on the surface. You don't quite need an impactor, a physical kinetic impactor. And I must also
and I think
mention,
you could save weeks if you could hit it with a light beam instead of sending a spacecraft out to its vicinity. Also, if the laser is on the dark side of the moon, then you wouldn't have the threat to other nations that there would be if it was, say, in orbit or something.
Well, I'm glad you brought that up because, again, I think perhaps Nahum or somebody else in this group were in review when we talked about the lunar sentinel, the idea being putting a bunch of high power lasers on the moon. But there are difficulties with that too, in terms of seeing how can you continuously see an object.
Half the time it would be out of the targeting because it's on the wrong side of the moon.
Yeah,
you don't want it there. So the
difficulty.
problem on Earth is that you have the atmosphere, as you mentioned. The problem in space, even orbiting, even if you can build it, is that you have a maintenance problem. Maintaining your device for years and years and years is something that's much easier to do on the ground. And so, putting it in low Earth orbit all the time, that's a maintenance problem. The moon is probably not a good place for dust either. But in answer to your question, John, the 30-meter telescope, for example, would be an example of the largest, really nice optical quality system. And you can very easily take a fraction of a milliradian laser beam at any power and map it onto the 30-meter telescope. And then you can calculate from pure physics, that has nothing to do with policy, simply physics problem of what the spot size would then be at 1 astronomical unit or a million kilometers or whatever unit you want. And then you can estimate how much energy you need in that laser beam to do the job. And of course, the problem is if it's on the ground, then it's also half the time not going to be available to aim where you want to aim it in space. So you have multiple problems.
But if you have several months, even if you can only hit it with pulses half the time, that might be enough time to divert it enough to miss the Earth.
Granted, but I think there are some studies on these
Yes,
points.
yes, there are
Livermore has
several.
done studies. I don't know about Los Alamos, but I know Livermore has.
Yeah, Ken, I think
That's
that maybe for next time we should try
Yeah.
to get Phil Lubin to present on that. I think
Yeah.
it's a fascinating topic. Did you have a
Yeah,
chance?
I talked to Madhu about this because remember last year we asked him, he sent his student from Caltech.
Oh, yes,
And
yes,
2
yes.
years we asked him, he said he was busy, so I didn't know whether we should ask him this time.
Okay.
But he did give a presentation with us to 2016.
Has it
Manhattan
been
Beach
recorded?
No,
Has it-
that one was not recorded.
Oh,
But Buzz Aldrin was
Yeah.
there. Buzz Aldrin, the astronaut, he was there in that talk, in Lubin's talk. So we'll try to invite him, but hopefully, he will have time.
I recall that
it is
Phil
an area.
Lubin-
It's an
Yeah,
area
says you
where
were there. You talked to him. You talked to Dr. Lubin and then followed him to the parking lot.
I've also been involved with space-based solar power studies for years. So there have been numerous studies, and I've been involved in a number of them, both at Boeing and back in my student days at NYU, and more recently, consulting for NRL. And so a lot of these issues about how do you get these things up to GEO, how do you maintain them over their lifetime? A lot of all these are incorporated in the study. So these issues being addressed. So the good news is there is work on very large sources of power in geostationary orbit, constellations of satellites that are ongoing. And the TRL level, the component TRL levels are high. The system TRLs are medium or low because nobody's built anything that size. But and I think Phil's had some conversation with John Mankins, and Phil's original idea was to put the laser array on Earth, and I think he's warming up to the idea of putting it in space, both because of the better duty cycle, and also you don't have to contend with the atmosphere. So I would say the biggest challenge of harnessing this potential of large solar collectors in space is, as I believe Dr. Worden has said, and he that there is the power densities for the solar power studies are relatively low by design, but in order to have a well-collimated IR or optical beam for asteroid deflection, you're now talking, and as well as Phil Lubin's idea, and you're now talking about weaponizable power densities. So this is in my opinion, this is not something we ought to rush into or shy away from, but just quite the contrary. There's all these different stakeholders for large-scale directed energy systems in space, and we got to get everybody talking. And so seminars like this are perfect. We got to do more of these. I also want to make a plug for the National Space Society, which has been instrumental in getting a lot of these experts together. I'm president of the Los Angeles chapter. If you want to know more, Ken could give you my contact information. But the conference they have an annual conference in a different city every year, and they have sessions on all of these issues. I've been involved in the solar power session, and Madhu actually is our regional board member. I think your term is coming to a close, this member, but you served a term for 2 years as representing the Southern California region on the NSS board. And Madhu and Nahum and I have all spoken at their annual conference. This year, it's usually in May, and this year it was going to be in Dallas. It was canceled because of COVID. There may be a lower scale online event next month. But next year, assuming things are sort of back to normal, it's scheduled to come back to LA. So might want to keep an eye on that and see if it's an opportunity to get together and discuss these matters further.
The National Space Society did host a planetary defense session. I think Nahum was part of it. Am I right to think that, Nahum? You ran a program, a session on planetary defense?
Yeah, so they invited me to give a 3-day series of talks to students, actually. I didn't have a technical talk. I had basically given my 3-day class, my 1-day class over 3 sessions. So, and I was part of the organizing discussions that we held at the time.
And,
so,
the year before that, the 2 or 3 years before that, when it was back in Los Angeles, I ran the session in planetary defense too. And we had Bill Ayler and Paul Choders and the others in a nice panel. So, so the National Space Society, if you go on their website, you'll see a part of their library is devoted to planetary defense. They've pulled up the most recent works. I must also mention that the online meeting is on July 16th, and they have lined up luminaries from various fields, a very broad section starting from lunar exploration to science and various technologies. The leaders are all coming up to talk on that online session, July 16th, I think. So you may want to take a look at that.
okay, can you send a link or something like that?
Happy to do that.
Okay.
I had a question for Professor Yoshikawa. You know, when I saw the slides, I was puzzled that the density is so low. And if I remember right, also the spin suggested that the thermal emissions of the surface seem to vary rather significantly during the rotational period. Again, wondering if the low density is due to hollowness, or did you have some thoughts?
Yes, I think there are 2 reasons. One is material itself is very porous, very low density, but maybe inside of Ryugu there will be large empty spaces. But we don't know. Yes, very low density. Yes.
Maybe Alan has something to say about it.
Well, I'm guessing that it's a mixture of macroporosity and microporosity. So as they said, the porosity is over 50%. So it's a combination of the two, and it's not possible to say in advance what the proportion of each is. But I'm guessing it's mostly microporosity rather than macro. But I'm sure there's a significant contribution of both.
Hollowness. Okay.
Okay, so are there any other comments and questions from the audience?
Yeah, this is Tom Treffner.
Okay, go ahead, Tom.
First of all, wonderful conference and gathering of great talks and experts. I do have a question for Dr. Yoshikawa. Hayabusa was incredibly successful. As a retired engineer, I'm particularly fascinated by the whole idea of a fleet of vehicles working in a coordinated fashion, and it was obviously very successful. In particular, Dr. Yoshikawa, perhaps you could say a little bit about the individual automation aspects. For example, the little free-flying camera that was set loose to watch the explosive activity, was it fully autonomous and managing its own orientation to keep on target, you might say? That was a very nice bit of engineering. Can you talk a bit about that, perhaps? That was for Dr. Yoshikawa. Thank you.
Yes, I understand your question. The small camera, DCAM3, is very small one. So it cannot control its attitude by itself. So when we release the camera is just spinning. So attitude was kept by the spinning. So only this. And the camera has two, the DCAM3 has two camera systems. One is the analog camera, and the other one is digital camera. So we use both camera to observe impact experiment.
I see. So basically, the camera was in spin axis controlled, and it was on target in that axis for the explosion. Very good. And could I ask a quick follow-on too? For the various vehicles, whether it was the camera or the rovers on the surface, did they maintain continuous, or did they maintain contact with the mothership for quite some time, even after the official end of the primary experiment?
Yes. For the mascot lander, the operation continues just 17 hours. So after that, we cannot we couldn't make a communication with mascot. And as for the small rover, Minerva 2-1, I think we were able to communicate for 1 month or 2 months.
Very good. Well, thank you again, and happy landings at the end of the year.
Thank you very much.
Thank you, Tom, and Dr. Ishikawa for the answers. Anybody else who wants to chime in here?
I think I have a question, Dr. Yoshikawa. Is any further missions to explore asteroid or comet from JAXA, from your group?
Yes. Now in JAXA, we are planning MMX mission, which is a Mars Moon sample return mission. So this is not the asteroid or comet. However, we are discussing another very small mission called Destiny Plus, and the target is a Phaeton, but in this case, just a flyby or Phaeton by very small spacecraft.
Ah, nice. Okay. Very good. When is it going? When is it planned to be? When is it scheduled to be built or launched, do you think?
Yes, maybe the launch is after 2025 or so.
Okay, so it's in the planning phase.
Yes.
Okay, great. Anything else from anyone?
Just
if I may ask Jennifer a question dealing with the law, which is obviously very important in these matters, I have learned over the years. Jennifer, did you want to tell us anything about comparisons to how we utilize the Antarctica, and if there are any parallels with going outside into space and dealing with some of these issues that came up?
Well, the only parallels that I found, it wasn't with Antarctica, a lot of the sea conventions and dealing with this, the shelves under the sea. And that's kind of where the international treaties have kind of looked at a comparison. And I didn't look into the Antarctica Treaty, so I can't speak to that, but it's been mostly the kind of the comparison for the outer space treaties has been the sea conventions.
Actually, Jennifer, I was about to, you see now Dr. Yoshikawa and OSIRIS-REx, they demonstrate they can do it and get a sample. If some company, billionaire, they, spend money on spacecraft and get some material back in the orbit or back to the Earth, and they are trying to sell something, is it something allowed or is still an issue?
As of now, well, it's hard to speak for different countries because the way the United States has interpreted it, when you go up there, if you collect something, if a private company goes and collects something, that's theirs, whatever they're going to do with it. And I think it's actually been called, that part of the law has been called the Finder Keeper's Law. When countries join a treaty, when they ratify it and choose to be bound by it, they actually regulate it in their own country, how that will play out. And so other countries might take a different view. And I mentioned the Moon Treaty as well. There are countries that have ratified that and have agreed to be bound by that. I can't remember offhand which ones are, but those countries actually have been agreed to be bound by a treaty that prohibits them from harvesting resources and without the general consensus of the international community.
So you are saying if somebody in Japan, a billionaire, is his business and get some money, he can do whatever he wants. But if it's JAXA, they have to be bound by the treaty because Japan is one of the signing party of the treaty.
Wait, I'm sorry. Which treaty are we talking about?
I mean,
there's the Outer Space Treaty. There's the Outer Space Treaty, and the Outer Space Treaty is much more vague. This is the 1967 treaty that kind of allows like freedom of exploration. And then there was the Moon Treaty that the parties are to it offhand. But those parties to that agreement, there's only like 4 signatories. Those parties agreed to harvest resources individually. They agreed that it would be done by an international mechanism. But again, China, Russia, and the United States did not sign or ratify that treaty. So that treaty really doesn't have a lot of input by it, depending on how their laws work within their own countries. Their citizens might also be bound by that if their countries have agreed to be bound by that and require their citizens to be bound by it. And that's what I'm saying. But I didn't go into each individual country. But I just kind of went into the United States. And but
There you go. Thank you.
Sorry,
Okay, looks like you're breaking out.
Reset for a second there. But sources. Am I back?
It looks like it now. Yeah.
Yes. I am having, all of a sudden about a half hour ago, it started to say my internet was unstable.
Oops. Okay, you seem to be back now, Jennifer, if you can hear us.
Okay. Yeah, so I don't know where I lost you, but essentially under U.S. law, if a U.S. company registered in the U.S. goes to space, collects anything, that's theirs. Other countries might, and their countries might have laws to enforced on their people, but as of now, the United States, if you go collect something, that's yours.
Okay. So I think people are starting to leave. So let me perhaps, if there are no questions in the queue, then let me just go over, sum it up, and do one more thing here. So,
Nahum,
yeah.
before you conclude, I want to thank all of you. It was a wonderful session. I know you skipped lunch, but that's the way it works. And I want to thank all of you for some very illuminating talks. I enjoyed particularly Professor McKeegan's talk on asteroids. I learned a lot, and I wish you all the best. And on to the next event. Thank you all, and please, Nahum, go on.
Thank you,
Dr.
Madhu.
Dr. Yoshikawa wake up very early in the morning.
Oh, that too, that's right.
That's right. We got Nicola at the end of the day and
Oh,
Dr.
yes.
Yoshikawa at the beginning of his day. So sounds like this is a truly international conference now where we can actually thank Zoom for getting us all together and talking all at the same time.
That is true.
Seem to working very well. So Madhu, thank you very much to you, first of all, for talking about the topic of lasers. I'm sure that that's going to be a continuing topic of discussion, both in your projects and in other studies. I enjoyed the idea of what you call the emergency threat level gates, a way to create different levels of response and awareness at different distances from the Earth. And also recognizing that the budget is always behind everything that we do. And so tapping onto the defense budget is something that if you can only convince one of those generals to give us a little slot within the defense budget, I think that would be a great idea. We are all trying to do that every year. And I think it does try to, I think it's on its way to get included in the, so it's called Space Force. I hear Space Force has a place for things like that. And so perhaps it will get more momentum. And also the Planetary Defense Coordination Office that was created at NASA, I think about 4 years ago or so.
That's
is
right.
starting to take up the issues of mitigation, not just detection and things like that. So, and they're talking about collaborating with the DoD. So I think it's coming. The momentum, I think, is there to, you know, bring it more attention and more resources so we can actually do something.
And you may know, Nahum, that Lindley is a USC alum, so we got to put some pressure on.
Exactly.
He's a wonderful man. Yeah.
He's like single-handedly enabling the whole. I think Lindley, he's the guy who coined the term planetary defense, I believe, right?
That's what I've heard also. And his slides from January 2020, I think, is a very good overview of where we are going. I think you may have seen them, Nahum. I've listed them in my slides, which I hope to hand over to Ken after I cleaned up a little bit. But again, thank you so much.
Thank you.
Thank you to all.
And then I'd like to thank Dr. Goldstein that told us how we can replace COVID with an asteroid in terms of getting ready for our. Oh, you're still online. Hello. I hope you enjoyed the rest of the talks. And I enjoyed the element of how to break down the risk that comes from multiple threats, right? Asteroids are not the only threat. It's asteroids and pandemics and other things. How do you actually rank the risk and the resources that should be allocated to dealing with those different type of threats, right? So sustainability obviously was a key message in your talk, and with emphasis on readiness, right? We would like to be ready ahead of the crisis rather than be responsive as much as we can. I'm sure that we'll be ready for the next pandemic, and this will factor into planning. Let's see here. And then Liam Kenny gave a super inspiring talk about his devices and the above ISS, I think it was called, or ISS above, and showing some cool videos about the meteors entering the atmosphere caught by a camera from the ISS. I think this is super cool. If you can only point that camera 180 degrees into space and show us an asteroid on its way in, that would be super cool. Maybe it's a future device that you can develop.
Yeah, that was a delightful talk from Ian.
Yes, I think I'm going to get in contact with him because we are both giving talks at schools, inspiring the kids, and
yes.
I think this is, I definitely have some stuff to learn from him. And then Phil gave the rundown on the movie that's going to be ready, I guess he said, in a couple of weeks, essentially, and released commercially in October. So I've seen a good part of it. I kind of know how it looks, and I think it's going to be an exciting educational experience to see this movie. So I think he has left the conference, but thank you to him. And also thanks to Nerida for the description of Goldstone. I think it was a very nice overview of what that observatory is doing and the effort of characterizing those objects by radar. Fascinating series of pictures that tell us a lot about these objects. And it would be cool to catch a ride on an asteroid, as she suggested, you know, one of those futuristic things, hike on an asteroid. I think it would be a cool idea to catch one of these objects.
That's right. Have you been to Goldstone recently? Have you been there?
No, I have not been there.
Well, it's been a long time, but the dish that she talked about was fascinating. To be able to go up, climb on top, and go onto the horn, it's pretty dramatic. And you know, I have a special connection to that place because Ed Recton was my mentor in school, and the road that leads to that antenna farm is named Ed Recton Road. Did you know that?
I did not.
Yeah, it's, I mean, and Ed was a fascinating person to deal with in school, and he used to make, you know, he started the systems architecting program at USC.
Mm-hmm.
And he had several heuristics of his own, one of which was that if you had to get some things done in a certain amount of time, the amount of time it took depended on the number of people involved in the project. So he always said, keep your projects small. Did you get it?
It was an inverse relation to the number of people.
That's right. That's right. I'm told that Nob Augustine also had a heuristic like that.
So he's an advocate of single-handedly running a project. Okay, and then Kevin McKeegan was an interesting talk. I think that it's really cool to have someone who has an asteroid named after him, which is cool. I didn't catch the number of the asteroid, but I'm sure I can probably Google this. And then also Alan Rubin gave insights about those objects and understanding the formation of the solar system. In fact, how to learn from these objects about how the entire solar system was formed was a cool thing to know. I definitely am going to plan another visit to the Meteorite Gallery. Sounds like it was updated since the last time I was there. And I'm going to make sure I'm going to go there on a Sunday afternoon so I can actually meet with one of those scientists.
If you tell us in advance, we can probably make sure that one of the real scientists is down there rather than a graduate student.
Okay, yeah, so we will coordinate with you. We'll definitely tell you that some of us are coming. And I'm looking forward to a visit after COVID. And also, it was interesting to hear about having some space dust in your salad. I didn't realize that that's something that could happen. It kind of reminded me Carl Sagan saying that we are all made out of stardust. So we made out of it and we eat it, I guess. So that's a cool thing that I learned today. Also, the recognition that the people who live at Chelyabinsk were kind of lucky that the asteroid entered shallow and exploded at a high altitude. So the shockwave was not that humongous. If it had penetrated at a steeper angle, could have been a much worse day there on this city. It was a good wake-up call, and I think this was one of the events that started the Asteroid Day. I think it was created the year after, or either the same year or the year after the movement of Asteroid Day. The yearly event was created after Chelyabinsk in commemoration of Tunguska. Let's see here. And then it was interesting to learn that some of those asteroids actually did exhibit, I think it was an undifferentiating process or differentiating process where the metals sank to the core and the surface shows the chondrites. So that's something that I learned. Some of them are undifferentiated and some of them are more of a mix of those materials, and this was exhibited in the pictures. And then also there was a question here. Okay, that question was answered. Okay, so the talks by Jared and Jennifer, I'm hoping that they're still online. Are they, any of them are still online?
I'm still here.
So actually I had a question. Who owns space junk? Non-cooperative objects, who owns them? Do they have any owner?
Well, if you launch it, if you launch a satellite and then, you know, it comes to the end of its useful life, and so then it just, you know, I think my understanding, and I'm not a scientist, my understanding is it does have a propulsion enough to get it out of the orbit to hopefully get it away from everything. But if that dead satellite then goes and hits another satellite, the person who launched that still owns that satellite. So they're still responsible for the damage that their dead satellite, for lack of a better term, causes. And the person, I mean, the company and the nation state that satellite was launched from. So if somebody launches it from the United States, ultimately, under international law, the US is responsible, but the US regulates it here so that, you know, obviously the company is then responsible to the US. So that, because the international, when you do the international treaties, those are all by agreement, and that's what the United States has been agreed to be bound to. But yes, the space junk, you're still responsible for anything you put up there.
Okay,
And
so that brings another
question, if I could.
You may know that we are starting to move things around in space, and that there are some systems that can act as tugs and remove them from orbit. Hopefully soon we'll start doing that.
Okay.
Question here, if I could. Quick question, if I could. Just following on the question on who owns the debris, you might say. I wonder if there's any maritime equivalent to a possible future business for salvage companies collecting derelicts and making money from it.
Yes, there are.
I think so.
There are companies that are created to attempt to collect space junk and use it as countermass for some space operations.
Well, I was thinking a little more about actually on orbit. You know, this is obviously not today or anytime soon, but as business gears up and Mr. Musk has a lot of valuable gear circling around there that eventually becomes dead gear. I wonder if there will be salvage companies in orbit collecting. You know, I'm thinking a future movie perhaps.
There are actually projects. I was part of discussions of a project where you would kind of snip the solar panels from a defunct satellite and create a inventory of functioning solar panels and can hook it up to another system that would be either already in space or launched from the Earth without those. So there are some ideas that are floated around to do something like that.
And lots of opportunities for the legal system to maybe prevent or promote it.
Right. Actually, I had a follow-up question for Jennifer in terms of secondary damage. So let's say there was an explosion by a satellite, it broke into a cloud of smaller pieces that are hard to track. Is there a responsibility attached to those secondary parts that are floating around space in big clouds? Sometimes it is intentional, as we know. Sometimes it is unintentional.
Well, and I think that comes down to the typical lawyer answer. It depends, because, and I mentioned earlier what the Chinese satellite that was blown up, and that and all types of debris still up there running around that it could run into things. So, but yes, technically, if you could prove that their debris caused damage to your satellite, then they should be liable. But the question is, if it's a 1-2 centimeter piece, how you have to be able to prove that it's their fault. So there's still a liability part. And the thing is, the larger satellites, 2 defunct satellites running into each other, or 1 defunct satellite running into a live satellite, that's easier to track and prove. But if you've blown something up into bits, and it's just the little bits that cause the damage, how do you prove that came from this Chinese satellite, or or whoever satellite it is? And that's something. So you still have to, when you go to the international community to bring this claim under the convention, you still need to prove liability and prove that they caused it. So that's kind of where you're going to run into problems because it might be just hard to prove. You're not going to have a site inspection like you would here with an aircraft accident.
Okay, yeah, so it's some kind of technical difficulty to demonstrate that the piece came from a known object. But if that would have been possible, then there would be a liability attached to the damage that it would cause.
Yes.
Okay, good. And then another question that I had, are there any commonalities in addressing space debris and asteroid concerns?
Well, I think, and as Jared and I were discussing earlier, I think if you actually are starting the asteroid mining, you're going to, you're going to have to launch the vehicles into space. You're going to be bringing things back. You may be trying to move things around. You're trying to extract things. So you're actually going to create more traffic, and you're going to create more issues. So there's a lot of different liability issues that we probably don't even know about yet. And they're going to be within the same framework that's already there for space debris and space launches. So I think really it's the increase of space debris where you have the asteroid mining and the additional traffic that's going to cause kind of what the, that's kind of the commonality there. And really the mining could damage the satellite, and see, it's just really increased traffic. It's like the 405.
Mm-hmm. The other dragon, Jennifer and Mahon, is planetary protection and contamination. It is an issue that rears its head ever so often. And I've been in the traffic sometimes, one time with the Vatican about this issue. And it can be protracted and quite difficult to resolve. I mean, JPL is getting the next roll ready for flight, and they are decontaminating it right now. It is a process that is very stringent, and yet reverse contamination would be a big issue.
Sure, yeah, that's true. Okay, and so I think we are ready to conclude. I have a few comments to make and then do one more show here. One of the things that seems to be coming back a few times in the recent past is the meaning of near-Earth objects. Because people have the notion that near-Earth objects are always near the Earth, and that is not true. Actually, those near-Earth objects are far from the Earth most of the time, because they are traveling along the respective orbits, which places them at huge distances from the Earth. But they're called near objects because of some legend terminology, but they're really not near the Earth most of the time. They have the potential of coming near the Earth at occasions. And so this is one of the things that keeps coming back. They are not near objects in reality. Also, there's many things that we haven't touched today, and maybe this will be one of the topics for next year, is the ethical questions that are kind of hard to discuss, but should be discussed. For example, out of maybe around 200 countries, only about 10 of them can launch anything to space. What will the other countries do if anything comes to hit them? Are we going to go save those countries? Who is going to pay for that? Things like these are questions that should be asked and addressed within an international forum, I think, if we want to keep the world safe rather than just your own countries, right? So these are some of the ethical questions. And let's do as a final step here, just a reality check as to what's going on around our planet right this minute. So I'm going to share my screen here. Give me just a second here to do that. And I always like to share my screen to see what's going on around our planet as we speak now. So I'm going to do that now. Hold on one second. Okay. Share screen 2. There we go. Okay, can you see my screen now?
Yes.
Okay, so what I've done here, I went to the JPL website. It's called CNEOs, JPL, NASA Gov, close approaches, and I'm basically just checking what's going on around the planet today. Today is the 27th, and there's 3 objects that are flying next to our planet. Here is one, a small one, between about 8 meters and 17 meters, that is flying around the distance to the moon. If it were 17 meters, it's about the size of Chelyabinsk object. And it is an object that was discovered this year. We can go and check when it was discovered and see how much of an alert existed here. It was first observed June 17. So 10 days ago. If that has been at Chelyabinsk, a 17 meters object headed into a city, we would probably have to do a civil defense type of action. Here's a few of them. Some of them are quite large. Here's another couple of objects that are 2 or 3 lunar distances away from us. Here's a fairly sizable one that can destroy a country. It's going to pass by us in the next couple of days. So June 29. Let's see when this one was discovered. It was discovered in mid-May. So about a month. Again, not much time to do anything about an object like that. And that's a significant damage on the ground. An object 100 meters in size could probably destroy a small city or a large city, and probably will not enable to come back to that city for quite a while. So these are all realistic objects that are going to be zipping by our planet in the near future. So this is just a reality check. It's part of those 23,000 objects that we are aware of today. And except for a few of them, they were all fairly recent discoveries, which means that we ought to be thinking about methods to counteract surprise objects on this table. So with that, I'd like to conclude. It's just part of the reality that we live in. We live in a shooting gallery. There's going to be hundreds of thousands of these objects in the future. And it's good that we are holding those conferences to promote general awareness on the topic. And I'd like to thank again to all of the panelists and the participants. If anybody has a last minute comment, and if not, I think we can conclude the event. Ken, do you like to say anything about AIAA?
Oh, yeah, thank you so much. AIAA really appreciate, and there's a great interest in this. So AIAA will continue to support and develop the related program and events. And finally, quite some of the speakers give the permission, so this recording will be posted online. So more thousands of people will be able to view the exciting discussion and the presentation today. So really, thank you so much on behalf of AIAA to send you that speaker section.
Okay, and thank you, Ken, for organizing this event. We were communicating over several months, and you did an amazing work putting together an excellent set of panelists with very informing presentations. I myself learned a lot, and I guess this time everything is recorded so it can be watched later on and contribute to the general awareness, which is an excellent thing. So with that, I'd like to thank everyone, and I think we can then conclude the event.
Thank you all.
Thank you, everyone. Talk to you soon, and stay safe.
Thank you.
Thank you,
Bye-bye.
Madhu.
Thank you. Bye.
Thank you. Bye-bye.
Thank you very much.